So this is take 2 of this video. I actually recorded this one already, and shout out to Danielle for pointing out a mistake. So now I'm hopefully fixing that in this video. So this video we're going to talk about the ideal gas law, but before we do, we are going to go over the molar volume of a gas. So this is a little shortcut that kind of bypasses the ideal gas law. So I'll talk about this first, and then I'll show you the ideal gas law next. So the molar volume of a gas just says that any gas at standard temperature and pressure, which as you can see here, standard temperature and pressure is 273 Kelvin in 1 atmosphere. 1 mole of any gas at these conditions will have a volume of 22.414 liters. Doesn't matter what type of gas, so you can see here we get helium, chlorine, you can have carbon dioxide, oxygen, it doesn't matter. They'll all have essentially the same volume, or very, very close to the same volume, so we just go with this number. So if I ask you, the volume or the number of moles in a gas, and I say it's at standard temperature and pressure, you should actually skip the ideal gas law equation and then just use this relationship. It'll save you a lot of time. And then remember, 273 Kelvin is 0 degrees Celsius. So keep that in mind as well. So the ideal gas law equation here tells you the relationship between pressure, volume, temperature, and moles of a gas. So you see the equation, PV equals nRT. Some people call it the PIV-NERD equation. Just a fun little way to say it. When you use this equation, pressure has to be in atmospheres, volume has to be in liters, number of particles has to be in moles, temperature has to be in Kelvin, and then there is this R value called the gas constant, ideal gas constant. And it's just this number just kind of glues the rest of the variables together. And it does have this large unit here, liters times atmospheres divided by moles times Kelvin. It basically just allows you to cancel out all the units that need to be canceled, and it'll get you whatever unit you need. So make sure you actually do write this down in your work and show your units canceling, and I'll demonstrate that here on the next slide. The one thing I want to point out though before I move on is that when you have two problems, you got to figure out whether it's the combined gas law problem now or the ideal gas law problem. And my hint on that is if it has moles in it, I guarantee it's going to be this equation, because the combined gas law does not have moles in it anywhere. So if you see moles in the problem, you know you're working with PIV-NERD. Also, the PIV-NERD equation has 1 pressure, 1 volume, 1 moles, 1 temperature. So if you ever see a scenario where it says like the pressure changes from 1 atmospheres to 2 atmospheres, you know you're working with the combined gas law equation. Or if the temperature changes, the pressure changes, the volume changes. If you're given 2 of any of those variables, you're definitely working with the combined gas law. But if you're only given 1 of each of those, it's probably going to be the ideal gas law equation, because it tells you how they're related in one scenario, not how they change from one to the other. So in this type of problem, you'd look at it, you'd say at STP you got 1.52 moles of gas. What volume is it? So you'd be tempted to fill all of this out, use this PIV-NERD equation here. Standard pressure is 1 atmosphere, and here I'll get my pen out. Let's see if I can get that going. So the pressure, is 1 atmosphere. The volume is what it's asking for. Tells you what the moles is. Let's see here, temperature, standard temperature is 273 Kelvin. And then that R value, the 0.821 and all the units. You'd be tempted to do that, and you can do it, and it would work. So you could solve for V by dividing by P onto this side. But if you remember, 1 mole of any gas at standard temperature and pressure equals 22.414 liters. So we go back to that side, so 414. I was blanking whether it was 141, but it's 414. So 1 mole equals this many liters. So with that knowledge, we can just set this up, 1.520 moles. Doesn't matter what type of gas it is. We bring moles down, we put liters on top. 1 mole of any gas at STP is 22.414 liters. And we can solve it like this. So we don't have to do any of this. It's a lot quicker to do it like this. So then we type it out. Get my calculator out here, 1.5 1 520 times 22.414. We've got 4 sig figs here, so we round this to 34.07 liters. So it's that easy. And again, if you want, you can plug in the numbers we know here, solve for V. You should get the exact same answer. So don't feel like you have to do it one way or the other. It's just knowing this trick will save you some time on a test or on a worksheet. So now this one, it's not at standard temperature and pressure, so we are forced to use this equation. So this one's saying, what is the pressure? So we're going to be solving for this. So we can divide V to this side, get rid of it over here. So now here's our equation that we're going to need. So pressure is the question mark. Again, remember, it doesn't matter that it's CO2. All gases behave the same. If the gas has the following conditions, so volume 1.250 liters, we have to convert this to Kelvin. So we do that, 85.475 plus 273. So this ends up being 358.475 Kelvin. The R value is 0.0821. That's liters, atmospheres, divided by moles, Kelvin. Where's our moles? Okay, so here's our moles. Whoa, what just happened? I pushed a button. Okay. 0.98754 moles. So now we have everything we know, everything we don't know, and we can plug it into this equation. So pressure equals our moles, which is 0.98754 moles, times the R value, 0.0821 liters times atmospheres over moles times Kelvin, times my temperature in Kelvin, 358.475, that's Kelvin, divided by volume, which is 1.250 liters. So now you can see here the moles is on top and then moles is on bottom of the fraction. Kelvin is on bottom, Kelvin is on top, it cancels. Liters is on bottom of this whole big fraction, it's also on top of this little fraction, so they cancel. I am left with atmospheres, which is great because I am solving for pressure. So if I type all this in, 0.98754 times 0.0821 times 358.475 divided by 1.250, and that ends up equaling a pressure of 23. And I gotta check my sig figs here, 4 sig figs, 5 sig figs, 5 sig figs. So we're left with 4 sig figs here. Don't worry about the sig figs of the gas constant. So then I would just go 23.25 atmospheres is my pressure here. So it's as simple as that. Just take what you know, plug it into all your variables here, solve this equation for what you're looking for, set it up, solve it, and you get your answer. And then just check your units, especially like check this, because if you look and you're like, oh, Kelvin cancels, degrees Celsius, wait, and then you'll be like, oh yeah, I've got to convert this to Kelvin. It's a great way to like catch yourself if you forget to convert to Kelvin, because that is the #1 way students get problems wrong in these, or answers wrong in these types of problems. The next problem here says, what is the pressure of a container of methane if it has a volume of 53 milliliters, contains this many moles, and it's this temperature? This is the mistake I made when I did the video the first time. This is already in Kelvin. You can leave it in Kelvin. So my temperature is 75.3 Kelvin. We have 0.675 moles of gas, 0.0821 liters atmospheres divided by moles Kelvin. Volume, though, It's in milliliters. 1, 2, 3. We move the decimal over. We have 0.553 milliliters of liters of gas. We convert it from milliliters to liters. It's again asking for pressure, so we solve by taking the volume, dividing it away to get rid of it on this side, and then you set it up in the same way. Pressure equals my moles, 0.675 moles, times the gas constant, times temperature, which it's already in Kelvin, so we just get to roll with it, divided by the volume, 0.553 liters. So let's type that in, times 0.0821 times 75.3 divided by 0.553, and we get a pressure of 3. So everything's 3 sig figs, so we'll go 7.55. 55 atmospheres. We'll round that to 3 sig figs. And that's that. And that is the last type of problem. Now both of these examples, though, solve for pressure. Let's go ahead and erase this. Let's say that they asked for volume. Again, if they ask for volume, to solve for volume, you divide pressure to the other side, you get rid of it. So that's an option. If they ask you how many moles of gas are in the container, to solve for this, you would take these and divide them over to this side. So RT just divides away from your unknown. So then PV over RT equals N. Again, pick any of these. You're never going to solve for the R, so don't worry about that. But if it asks you to solve for the temperature of a gas and they give you the pressure, the volume, and the moles, well, you just divide N and R to this side to get rid of them. So T equals PV over NR. So just make sure that you can do the algebra on that to solve for whichever unknown you need to do. And that is it for ideal gas law problems.